Welcome to the Rare Earth Exchanges podcast, where power, politics, and the world's most coveted materials collide. Rare earth elements power the backbone of tomorrow's most critical technologies. With China dominating global production, the U.S. and its allies must align strategically to ensure a stable future. This urgency prompted tech entrepreneurs Daniel O'Connor and Dustin Olson to launch Rare Earth Exchanges, a news and insight platform built to equip stakeholders and decision makers with the tools and intelligence needed to reduce dependency and build prosperous resilience. Let's get into it.
Hi, everyone. Welcome to the Rare Earth Exchanges podcast. I am Dustin, your host, joined by my co-host, Daniel, and we have our special guest, Lynn Ding, who is a chemical engineer and is going to talk to us more about the separation process in the rare earth sector. Lynn, welcome to the podcast. How are you doing?
I'm very good. Thank you. Thank you inviting me here to recording the podcast.
Absolutely. Lynn, to kind of kick things off, to help introduce you to the audience, can you give us a quick summary of your background and how you got started in chemical engineering?
Okay, so I'm a PhD in rare earth separation and also extraction. I just graduated from University of Toronto last October, and I'm actively looking for some process engineering jobs in Canada and the US. And I choose chemical engineering because in senior high school, I'm interested in the chemical reactions, and then I choose chemical engineering for my undergraduate. And during the undergraduate, I realized that the experiment we do in the lab looks beautiful, but as we scale it up in the industrial, it might cause severe pressure to the environmental problems. So now I realized I need to do something important or meaningful to the society. So now in the PhD, I start to pursue my hydrometallurgy PhD degree. It's because I know that the metal extraction and separation is very energy and chemical intensive, and the waste can put a lot of pressure on the environment. So I choose the hydrometallurgy, and the reason why I choose rare earth element is because currently the popular critical metals, we can say battery metals, including lithium, cobalt, nickel, manganese, and also the manganese metals, the rare earth elements. And among all of these metals, the rare earth element faces the most high energy, most energy intensive and chemical intensive, and also will need to deal with the most wasted treatment. And also the rare earth face the most challenging technical hurdles, for the separation. I choose rare earth because I know it's very important, and I like to do something that is difficult. So I asked the professor to give me this rare earth project. So now I'm going to the area of rare earth. I think that's a summary.
All right, I will jump in here. Very important. We're so excited that you've gone down this path because it's needed. We write a lot about the need for more chemists, engineers, metallurgists, and so the fact that you've studied this and gotten your PhD is very exciting. We picked up your paper and we did an article about it, so that's how we got to know you. Do you want to maybe just explain at a high level for the viewers, what was your paper about and what did you discover?
Do you want to discuss about the extraction or the separation, because they are different?
Let's look at first the extraction, okay, and high level.
Okay.
To start.
Okay. So we got a new rare earth resources from the North America, like Chile, and we start to discover what minerals it has and what kind of metals it has, and we find that there are rare earth elements on the surface of the clay. And we investigate a very mild leaching process, like using pH larger than 3 acidic solution, and also using ammonium sulfate as lixiviant agent to leach the earth from the surface of the particle at room temperature and the atmosphere. And then we also optimize the process. So that was the engineering part. For the scientific part, we do investigate the mechanism that how the rare earth absorbed on the clay and how the rare earth dissolved from the clay. So that's for the extraction part.
Excellent. And the extraction happens to be a key first big part of the problem. And then, of course, there's a separating each element away from each other and from the other material. So
yes.
What do you see first if we look at extraction and separation? what do you see as more complex first, in the
Okay.
lab and then in the real world?
Both in the lab and in the real world, separation will be definitely much more difficult than extraction for the rare earth element.
Right, right.
That's
And so with that in mind, what's your understanding of why separation is so difficult?
okay. So it's because the rare earth, it is a series of 70 elements they very close in the periodic table, exclude like yttrium and scandium. They may be a little bit higher in the location. They have very similar physical and chemical properties. I can just set an example. For example, we have 3 people here, and we are totally different. So other people can identify us very easily. But if we have 3 people, Japanese, Chinese, Korean, it might be difficult to identify them. And another case is we have 3 triplets. Like if we have 3 triplets, they look almost the same. They have almost the same appearance, so we need to check their fingerprint. Neighbor rares like twins and also triplets, their appearance looks very similar and they have very similar characteristics. So it's very different to tell them apart, and separating them even more harder.
Makes total sense. Makes total sense. So in your paper, how did that part of the experiment in your studies come along? Was there anything that you observed that was surprising? You all had a hypothesis and you tested and you did the experiment and you wrote it up. What could you share any notable findings that interested you?
Okay, my finding is that even though they have very similar properties, but we still can find some chelating agents. They have different affinity preference to the chelating agent. So this kind of chelating agent, let's say HEDTA, EDTA, DCTA, something like this can combine with different rare earth elements with different affinity. For example, the DCTA can combine, for example, we have one more of the neodymium, one more of the dysprosium. They are very important for the manganese. And they have totally different preference to combine with the DCTA or EDTA. The heavier of the rare earth, so the dysprosium will more likely to combine with the EDTA, but neodymium will be less. Because neodymium and dysprosium, they are far away in the table. Neodymium is light and the dysprosium is heavy. So their preference will be a lot different, like 10 times. But for the neighboring rares, for example, praseodymium and neodymium, these are also the manganese rares. Their preferences are very similar, only like 10% differences. So it's very difficult to separate the praseodymium and neodymium, like the twins.
Yes, yes. And we've heard that. So now, from that standpoint, there's a 1SX, they call it, a way that they go about separating. At the university where you're at, were you looking at other alternative approaches, or what methodology were you using?
I'm using chelation-assisted electrodialysis. So the chelation-assisted
Can you say that again?
Just what I said. It's chelating-assisted electrodialysis.
Okay.
So chelation-assisted, just what I say. We use EDTA or DCTA to combine the heavy rare earth element. And electrodialysis is a mature technology that has already been widely used in wastewater treatment like desalination. So we do some adjustment to this mature technology to apply this new technology to separate the rare earth element.
Okay.
So that is what I do. But I also know that there are some other research about, for example, the ion exchange. Some use that they are like design often sign some proteins as chelating agent for better selectivity, but I have like no idea how specific they are doing.
Right. Yes. Yeah. It's complex and we're not chemists, but we write about some of these processes and we've interviewed a few other people. What about in terms of the approach that you worked on? Can you speak a little bit about the energy involved, units of energy, and also environmental factors, just to have a better understanding of this process from your perspective?
Okay, so we use electrodialysis. The point of using electrodialysis is because we want to use electricity to replace the organic solvent. So our technology, we use water to replace the organic solvent. And we also use electricity to replace the very corrosive strong acid use. So we use water and electricity to replace the organic solvent and the corrosive, highly acidic solution. And for another key point for our technology is like we use less chemicals. And because we use less chemicals, So we will generate much less waste. So that is very environmentally friendly. It's totally environmentally friendly. No organic solvent, less chemical, less waste.
Very, very important. I mean, that's what caught our attention, to be honest with you, was that. And of course, these different approaches have not necessarily been proven at scale, right? But you got to start somewhere, right? So
Yes.
you want to talk about you finished your PhD?
Yeah, I finished like last October.
Okay. You've finished your PhD, and, what are, just out of curiosity, with other students, PhD students that are studying this, I mean, there must be a growing interest, right? Because the supply chains have to be rebuilt, right? We all know
Mm-hmm.
that mainland China has a monopoly pretty much on the refining or the extraction separation of these rare earth elements. So was there a sense at your university, is there more interest in this topic? Are there more people going into chemistry programs, for example? Is that becoming more of an interest in the university level, do you think?
The separation of rare earth elements come to the research like 5 years ago or 6 years ago, maybe 5 years ago, and all the funding is from the government. I remember there is a company like want to support the rare separation. They may find it's too difficult, or they may find that the payback period will be too long. They overestimate the difficulty of rare earth, so they just give up on the project. But the government sponsor a lot to the rare earth separation.
Yeah.
Canadian government do it, our University of Toronto do it, but right now I only know 2 groups doing rare earth separation in electrodialysis. There might be some other groups in the US or other labs, maybe most of in the US to do some other research like the protein synthesis or some ion exchange, but the scale is very small, not like AI or others.
Understood. What were the 2 in Canada? What are the 2 centers that are doing this type of separation?
One is our lab, like Azimi's lab,
Of course.
Azimi's strategic material lab, and the other is Arcan. I'm not sure, like Canadian government. They
Okay.
are on their own like research team, and
So-
we collaborate sometimes.
And there are a couple companies or organizations in Canada that are setting up rare earth separation refining operations, including Saskatchewan Research Council, right? So it's called SRC, Saskatchewan Research Council, and they have government funding in Canada, and they are actually separating rare earth elements.
Which type of technology are they using?
I think they're using SX, I think. Pretty sure. We can check on that.
Okay.
From your experience going through your studies, this is a follow-on question to what Daniel was asking.
Mm-hmm.
Are you finding more and more people being interested in being a part of the rare earth industry, either from like a mining separation perspective, such as yourself, or do you feel like they're struggling to gain students interested in the programs to learn more? Where do you find that balance to be?
Okay, I think for the rare extraction, like more companies, like startups, try to do some about extraction, but for the separation, not too much. Maybe because they haven't reached that stage to consider about the separation. They need to deal with the extraction first. Yeah, but yes, governments pay attention to both extraction and separation. And the universities, I did not notice that they are like pay more attention to the rare earths because actually the university should have funding from industrial or from the government. Only when government or industrial have interest in this type of research, then they will have money to give us to do it. Yes.
We have noticed we're starting to see a change in that effort from a government perspective. They're trying to reindustrialize their own countries to bring things in-house, so to speak. And so they need more talent. They need people who understand these things.
Yes.
Are you starting to see some of that show up? Obviously, I know here in the United States, a lot of businesses are getting funding to grow and scale their operations.
Mm-hmm.
Have you seen a trend towards universities? Do you think they're next in terms of getting funding?
Okay, so for the extraction, I see the trend. So for the extraction, many companies, they find, for example, new resources or some like in this area, in that area, then send this sample to our lab to help them to see, okay, could you help us to design a process to extract the rare earth element? The trend of the extraction is increased, but for the separation, not yet.
Understood.
Yeah.
Through the university program, have you guys partnered with other businesses to help them do the research, develop the technology?
Yes, so our lab will collab with some companies, for example, some engineering companies like the Hatch, something like this, and also collaborate with some mining or mineral companies to directly help them to design the process or optimize the process.
Okay.
Yeah, I hope more funding will go to the separation, because the separation is the point that you need to spend more money, more time to like break through, not extraction. Extraction is just acid, leaching.
So let's talk a little bit more about that. The extraction, from what I'm hearing, that's easy, right? We've been doing it for a long time. Separation, however, is not. That's a lot more complicated. What are some of the, let's first talk about what are the limitations you've found with separation, and then what are some of the breakthroughs you have discovered through your studies?
Okay, so the limitations, you want to say the solvent extraction or other technologies?
Just whatever you've learned through your research.
Okay, so for the solvent extraction, the limitation is like high demand of the chemicals, the solvent, organic solvent, and the chemicals. And for example, for the solvent, it is toxic, volatile, flammable. So we need to design very like complicated risk management, like VOC control system, something like this. And also because for the rare earths, it's very difficult to separate, and you need to reach like up to hundreds of stages. So this number is very like huge, hundreds of stages. Like, so you need a lot of solvents and a lot of acid. The process will be very, very like, the plant will be very, very big and very complicated. And you will generate a lot of waste because we use a lot of chemicals. The dealing with these waste is also a problem. The final waste will be like the salt solutions, the acid solutions, and also the solid waste, and might be radioactive. And how to deal with waste can also be a problem. And also the transportation of these toxic corrosive chemicals. So you need to find a plant that is close to the manufacturer that can give you a cheap acid and lower transportation fee. It's very, very complicated. And for my tech knowledge, the breakthrough is, there is a breakthrough for all technology, the selectivity. So, but selectivity is the most difficult one to break through, because right now we can only base on the low selectivity right now to design many different technologies. Can find some chelating agent that has very good selectivity, then we can decrease the number of stages allowed. Like it will be no problem for the rare separation. If you can find or design or synthesize a chemical or protein that can have very high selectivity, but now we cannot. So we can only base on our current low selectivity to design solvent extraction or electrodialysis or other ion exchange process. And for solvent extraction, I just said before, the bad thing is like the solvent and the corrosive acid. And for the electrodialysis, the chemical feasibility have been demonstrated, but for the economic analysis, like techno-economic analysis, we haven't done yet. And I'm not sure if it can beat the solvent extraction, but I'm confident about it, because after you optimize the process, you can decrease the cost in operation and also the capital cost, and also the most beautiful thing about the electrodialysis is just less chemical, less waste treatment. It will save a lot of money in the chemical and waste treatment, but it will spend more money on for example, the membrane cost, the electricity. But electricity is not such high if you choose a location like in Quebec, Canada. And for the membrane, I hope some labs can do research to produce or manufacture to investigate some.
A lot of information, a lot of interesting information.
Sorry, I speak too much.
No, I think it's educational to understand some of the nuances that go into separation. So a moment ago, you talked about being able to find a protein to help with the separation, but it doesn't exist yet.
It can be protein or it can be chemical molecules. like EDT or DCT, so it can be discover it or synthesize it, but we haven't found it.
So is the limitation, is it current technology, like we can't develop it, or is it funding and there's just not enough money to put towards that sort of research so that we can?
We can. For some biolabs that are doing such kind of experiments. For example, in the US, there are some labs doing that kind of research to generate to like cultivate batteries or something else to generate some proteins, and they use protein as as chelating agents. So for me, I use chemical molecules, ETA, DCTA. They use proteins as chelating agent to increase the selectivity. Yes, but for the chemicals, for example, what we do, we can just buy the chemicals very easily. But for their proteins, they need to cultivate batteries or they need to produce the proteins. It will be another tough job to do it. So it's more like it's so to scale them up. I think electrodialysis is much easier than the proteins to scale up, because if you introduce bio, there will be a lot of other tough work to do.
Yeah, so let's dive into that just a little bit more, this scaling issue, because when we're talking to a lot of people from universities, they do a lot of research, a lot of things sound great in the lab, but in terms of economically scaling a solution for commercial use is a bit hard. Hard because there's just not enough resources to even make it work, right?
Yes.
So can you give us more insight into how what you've been studying, what you know, how does that scale?
Okay. So for example, let's say the electrodialysis is what I'm doing right now. So for my electrodialysis cell is like very small, and we use constant voltage. So constant voltage is a version like how we operate electrodialysis. It's very safe because as the concentration of solution decrease, the current will be zero. So there will be no current. It's very safe. But for the industrial scale, they usually use the constant current, which means that if the concentration in the solution decrease, they need to keep the current at the same value. So in that case, the voltage will increase a lot. If the voltage increase like rapidly, there might be some risk like the fire hazard, some other dangerous things happen. So like first one is safety. In the lab, it's safe, but in the industrial scale, it might not need other safety control or risk management to make the process safe. Another one is in the lab, we use batch process. So in the chemical engineering, there is batch process and continuous process. In our small lab, we use batch process, and we can do the experiment day by day. We can test the stage. So, we have 100 stages, and we can test the stage one by one. But in the industrial scale, they need to use the continuous process to decrease the cost, like operational cost. So in the continuous process, you cannot do the stage one by one. You have to set hundreds of stages together, and they need to work together simultaneously. So 100 stages work simultaneously is very difficult to control all the stages. So in addition to the equipment to do the separation, they need a control system, like to control all the stages. And the control system is difficult to design because you have 100 stages, and you have a lot of pH to measure, you have a lot of concentration to measure. So design and application of the process control system will be another difficult thing to do. Because in our lab, we don't need to do, because we have person to control the process. We only have one stage at one experiment, so it's much easier. And that's the second one. The third one, okay, I think that's the two we need to consider: the safety and the process control.
Very interesting. And I could see definitely, 100 different stages would be a lot to manage, much less do it at a volume that would be economically viable for a business to adopt.
Yes.
So as someone who's looking at the research level, what do you think the industry sometimes underestimates about separation chemistry? Like where they may be misunderstanding something?
I think maybe overestimate, not underestimate. Yes, if they underestimate this technology, they do not need to do any research. They just grab this technology and use it, scale up it, and just do it. But if they overestimate it, they might think that it's too difficult for them to do it right now. Because if it's too difficult, they need to invest a lot of money, a lot of time to this, and they may, okay, we spend a lot of money, spend a lot of time, but finally we may fail. So they just give it up and do not invest it. Or maybe they did not overestimate it or underestimate. They just did not notice that problem. Because currently most companies in the US and in Canada or in Europe, they just focus on finding new resources of rare earth element and extraction of rare earth element. And after the extraction of rare earth element, they just sell the whole rare earth element to some companies to do the separation. So they haven't reached the stage to consider about the separation problem, but finally they will meet this problem.
Interesting. Okay, so your perception is that they take for granted, or they overestimate the ability to adopt some of this technology without maybe fully understanding its own limitations or things like that. Is that a fair summary to say?
Yes, yeah, I think so. But because for me, I think I kind of like to overestimate it because currently in our lab we only take like several stages separation, but in the real case we need to hundreds stages, and I cannot even imagine how I can do the whole 100 stages by myself too in the lab scale. So for me, I probably overestimated, but for the company, I'm not sure they overestimate or underestimate. They maybe just haven't noticed this problem.
Okay. And looking into the future, what are some things that give you hope or give you optimism about the future of rare earth processing technologies?
Okay, I think I'm positive about it because I'm finding that, as you said before, more fundings from the government to the industrial, and then from the industrial to the universities. So if you spend more funding to cultivate more engineers, PhD students, expertise, then definitely this area will be like very like positive to have better technologies in rare both extraction and separation. Definitely, because talented people will do a lot of work.
Yeah, we have the same optimism as businesses and governments become more invested in the need to restore their own domestic supply chains, that we're going to see a lot of renewed interest, renewed or even new companies being built to help support this effort. And we hope that that will transcend down to the university level,
Yes,
where people are learning the skills that they need to be a part of this industry, whether they're metallurgists, chemists, you name it.
yes,
So
and
we're looking forward to that.
yeah, and I strongly suggest to fund the collaboration between industrial and the universities. Because if you only fund the universities, we only have PhD students that have very limited industrial skills, and our thinking problem method will be different from engineers. So if we have engineers, PhD students, expertise professors work together, we can definitely speed up the research process and also think of better technologies. That is what I'm saying, what I feel, because for my own experience, I'm the only person do the old experiment in the lab, and I have very limited industrial experience. So I think if some people like join me from an industrial side, I think I can do the project much better than now.
Yeah, I think that's a great call to action. So we need more involvement from the businesses
Yes.
and universities together
Mm-hmm.
funding will be great. Having money to do this research would be great, but you need the experience of those who are out in the field, who've done this work, who can share their knowledge to help accelerate additional research. And so I would agree that collaboration amongst universities and the industry would do wonders. And we've reported on other businesses in Europe that have created those collaborations. They've publicly announced collaborations with other universities, and I think it's a smart thing to do. So hopefully we see that happen more sooner than later in other countries around the world, because the talent, sharing the talent, the knowledge will be extremely vital.
Yes.
So as we kind of come to the end of our show here, Lynn, if you were to just quickly summarize everything for us, What is one thing you would like people to understand about the research you've done, the work you're trying to do, and things like that?
I want people to know that separation rare earth element is very difficult, technically difficult, and the current technology for extraction is energy intensive, chemical intensive, and will generate a lot of waste. And my project will delete the use of the organic solvents and also use less chemicals, generate less waste. And I hope like governments, industrial can do sponsor more, like give more funding about the electrodialysis, and in addition to the research, but also to the scaling up and optimize the process.
I think that's a great summary. And Lynn, as we move on today, we do wish you the best of luck as you are trying to make your mark in society, as you were saying earlier, to make a difference in this space. We fully support that initiative that you have for yourself. We look forward to seeing other publications that you put out there as you continue to learn more and share with the world what you're learning.
Thank you so much, Dustin. I will.
Great. Thanks, Lynn. And thanks for being on the podcast with us today. It was very educational.
Thank you very much.